Fire and water. We treat them as opposites, enemies, as if it's simply obvious that one destroys the other. But it isn't obvious at all. Fire is a chemical process, a rapid oxidation reaction producing heat and light. Water is a molecule, two hydrogen atoms bonded to one oxygen atom. Why should one molecule, in any quantity, be capable of stopping a self-sustaining chemical reaction that can reach temperatures exceeding 1000 degrees Celsius? The relationship between fire and water is far more complex and far more interesting than the simple opposition we learned as children. And understanding it means understanding three completely different mechanisms that water uses to attack fire. Three separate battles happening simultaneously the moment water hits flame. The war between fire and water isn't a single fight. It's three wars happening at once. To understand how water fights fire, you first need to understand what fire actually needs to survive. Fire is not a thing. It's a process. A self-sustaining chain reaction that requires three ingredients in constant supply: fuel, oxygen, and heat. Remove any one of those three, and the reaction stops. This is the fire triangle, and every firefighting strategy in history is ultimately an attempt to knock one of those three sides out from under the fire. Water attacks all three sides, but its most powerful weapon is heat absorption. Water has one of the highest specific heat capacities of any common substance, meaning it takes an extraordinary amount of energy to raise water's temperature. It takes 1 calorie of energy to raise 1 gram of liquid water by 1 degree Celsius. That's already high. But the truly devastating number is what happens when water turns to steam. When water at 100 degrees Celsius converts to steam, it absorbs an additional 540 calories per gram. This is the latent heat of vaporization. It's more than 5 times the energy needed to heat water from freezing to boiling in the first place. And it happens all at once, at the moment of phase transition, pulling that enormous quantity of heat directly out of the burning material. When you pour water on a fire, the water heats up rapidly, then converts to steam, and in doing so steals a massive quantity of heat from the combustion zone. The temperature of the burning fuel drops. If it drops below the fuel's ignition point, the combustion reaction can no longer sustain itself. The fire goes out. The second battle happens in the air above the fire. When water converts to steam, it expands dramatically. A single liter of liquid water at 100 degrees Celsius produces roughly 1,700 liters of steam at atmospheric pressure. That enormous volume of steam displaces the air surrounding the fire. And since air is the source of the oxygen that fire needs to continue burning, displacing the air means displacing the oxygen supply. This effect is particularly powerful in enclosed spaces, which is why steam-based suppression systems are used in ships, server rooms, and aircraft engine nacelles. In an enclosed environment, the expanding steam can rapidly reduce oxygen concentration below the threshold needed to sustain combustion, roughly 15% oxygen by volume versus the normal atmospheric 21%. In the open air, the oxygen displacement effect is less dominant, but still real and still contributory. The steam cloud around a fire creates a momentary oxygen-reduced zone that slows the reaction even as the heat absorption effect is doing its primary work. The third mechanism is the most underappreciated. Water doesn't just fight the active flame. It changes the fuel itself. When water soaks into a burning material, wood, fabric, plant matter, it does something chemically transformative. It occupies the spaces in the material's structure. It coats the surface. And it raises the thermal mass of the material dramatically. For solid fuel like wood to burn, its surface must reach pyrolysis temperature, typically around 300 degrees Celsius, at which point it begins releasing combustible gases. A wet piece of wood resists reaching this temperature because the water in and on its surface is constantly absorbing heat and converting to steam, acting as a continuous thermal buffer. This is the difference between a green log and a dry log in a campfire. Both are chemically identical wood. But the green log is full of water, and that water constantly fights the heat trying to drive the wood to combustion temperature. The dry log has no such defense. Firefighters exploit this principle when they wet down vegetation around a wildfire perimeter. They're not trying to cool the fire itself. They're trying to raise the water content of the unburned fuel so that the fire can't easily ignite it when the flame front arrives. Fire and water have been adversaries for as long as both have existed on Earth. Lightning starts fires. Rain extinguishes them. Humanity learned to harness both, and in doing so, built civilizations. But the battle between them is not simple opposition. It is chemistry and physics operating simultaneously on multiple fronts. Water kills fire by stealing its heat, suffocating its oxygen supply, and transforming its fuel into something that resists burning. It fights with thermodynamics, with fluid mechanics, and with chemistry. 3 separate weapons deployed at once, each attacking a different essential element of the fire triangle. The next time you watch a firefighter direct water at a burning building, you're watching one of the most elegant multi-front chemical battles in nature play out in real time. 3 wars. 1 weapon. An opponent that has ruled the night since before our species existed. Water wins. Most of the time.